The massive breakers at the substation have just slammed open, cutting off the factory to save the rest of the grid from a cascading failure. But throwing that mechanical switch isn't the end of the story. If we zoom in to the microscopic level inside that breaker, we find a massive problem. At high voltages, when those heavy metal contacts violently tear apart, the electrical current doesn't actually stop. Instead, it rips through the air, bridging the gap with a blindingly bright plasma arc. Because the grid runs on alternating current, this plasma arc is riding a wave. It will only extinguish naturally at the exact millisecond the alternating current crosses absolute zero. And that exact microsecond, when the arc finally snaps out of existence, triggers a hidden threat. With the current suddenly gone, a massive new voltage spike instantly materializes across those newly separated metal contacts. Engineers call this the transient recovery voltage, or TRV. And its appearance ticks off an invisible race that will determine whether the wider grid survives. We like to think that pulling a lever stops the flow of electricity, but securing the grid comes down entirely to who wins the next single microsecond inside that breaker chamber. This microsecond race pits two opposing forces against each other: the rapidly cooling physical gap between the contacts and the surging voltage of the wider grid pushing back against it. The breaker's only defense mechanism is its dielectric strength. As the physical gap widens, the surrounding gas cools down, actively restoring the space's ability to act as a physical insulator. This graph visualizes that physical race. You can see the breaker's insulation strength curve rising steadily upward, but at the exact same time, the power system fights back, slamming that high-frequency transient recovery voltage across the same gap. The steepness of this voltage curve is the metric of destruction. It's called the rate of rise of recovery voltage, or RRRV. If that voltage rises on a faster, steeper trajectory than the insulation can recover, the two lines intersect, and the grid's voltage overwhelms the gap. When that gap is overwhelmed, the insulation breaks down. If the breakdown happens before a quarter cycle of the power frequency passes, it's known as a reignition. If it happens after that quarter cycle, it's called a restrike. A restrike creates a brand new arc, which means the breaker has to try to interrupt the current all over again. Multiple restrikes cause extreme voltage escalation, where each successive failure pumps more energy into the circuit until the physical equipment tears itself apart. The breaker must physically outpace the grid, restoring its internal insulation before the incoming voltage spike can deliver a killing blow. So what dictates how fast that voltage returns? The answer lies outside the breaker, in the macro topology of the surrounding grid. One of the most dangerous scenarios engineers plan for is the short line fault. When a short circuit occurs on a transmission line just a few kilometers away, the interruption traps electromagnetic energy on that short stretch of wire. That energy begins bouncing back and forth between the open breaker and the fault location, like a rapidly traveling wave. This chart shows exactly what that looks like. You can see the line-side TRV component oscillating in a steep, triangular, sawtooth shape. This traveling wave forces the initial rate of rise to skyrocket, creating an incredibly aggressive slope right when the breaker is most vulnerable. A second, highly deceptive hazard comes from faults that happen right next to a massive transformer. Transformers are naturally good at limiting the raw magnitude of a fault current, but their internal windings contain a physical property called strike capacitance, which stores electrical energy and acts exactly like a tightly coiled spring. Take a look at this simulation. When the breaker opens, that spring unleashes its stored energy as an extreme high-frequency voltage spike. The dark line representing the actual TRV curve shoots upward, violently breaking right through the established perspective standard TRV envelope, the red curve, meaning it easily outpaces the design limits of a standard medium voltage breaker. The layout of the copper, steel, and substations around the fault entirely dictates the speed and shape of the electrical weapon pointed at the breaker. If the grid's physical layout guarantees a deadly rate of rise, engineers have to figure out how to rig this microsecond race to guarantee the breaker wins. The first method is a physical solution, installing surge capacitors directly at the circuit breaker's terminals. By nature, a capacitor opposes rapid changes in voltage. As the energy rushes toward the gap, the capacitor absorbs a portion of it, forcing that steep, dangerous voltage spike to flatten out into a slow, gentle curve. This artificially drops the rate of rise, buying the hot gas inside the breaker those crucial extra microseconds to cool. But there is also a digital, algorithmic approach, known as controlled switching or point-on-wave switching. Instead of yanking the metal contacts apart the instant a fault is detected, a smart controller actively monitors the grid's alternating current and artificially delays the physical trigger. The controller is waiting for a reignition-free window. It calculates the exact millisecond to separate the contacts so that the eventual current zero happens when the grid's electromagnetic wave is at its weakest, least aggressive point. By deploying physical capacitance to slow the voltage down and precise digital timing to pick the safest moment to fight, engineers rewrite the physics of the breaker chamber, removing luck from the equation entirely. When we look inside that chamber under these controlled conditions, we finally see a clean interruption. The glowing plasma arc between the two metal contacts cleanly snaps out of existence, leaving behind a dark, rapidly cooling gap. The transient recovery voltage still arrives, but its curve crests safely below the breaker's established limits. The insulation holds. Zooming all the way out, the system remains stable. The compromised factory is safely isolated in the dark, while the surrounding high-voltage lines continue humming smoothly, completely unaffected. A successful localized blackout is the silent, invisible victory of a circuit breaker surviving a high-stakes battle against the immense power of the grid itself.